Infinity. A word that stretches the mind until it trembles. To gaze into the night sky is to feel its presence, a vault of stars without end, a silence that seems to extend forever. Mathematicians find it in the endless progression of numbers. Philosophers confront it in paradoxes that defy logic. Physicists glimpse it in the singularities of black holes and at the birth of the cosmos itself. Infinity appears everywhere, woven into our deepest descriptions of reality. And yet, perhaps it is nothing more than a mirage, a trick of language and imagination. For in mathematics, infinity is slippery, refusing to obey the rules that govern the finite. In physics, infinities often signal not truth, but failure, the breaking of theories at their limits. The Big Bang as an infinitely dense point, the interior of a black hole as an infinite collapse. Are these real, or signs that our equations have reached the edge of their meaning? If infinity is an illusion, then the universe itself may not be endless. Space may be vast but finite. Time may have a beginning and an end, and the fabric of reality may be composed not of limitless continua, but of discrete, countable pieces. The human mind may long for the infinite, but perhaps nature offers only finitude. So we must ask, is infinity a property of the cosmos, or a dream born in human thought? And if the infinite is an illusion, what then does it mean for our place in a universe that may not last forever? From the moment humans first looked to the stars, they were haunted by the sense of something without limit. The night sky was not merely vast, it was boundless. It stretched beyond sight, beyond thought, beyond measure. In every age, in every culture, the infinite lingered at the edges of human imagination, a mystery too large to hold, yet too alluring to ignore. The birth of paradox. The ancient Greeks were among the first to wrestle openly with the problem of infinity. Zeno of Elea, a philosopher of the 5th century BCE, devised paradoxes that still trouble us today. He argued that motion itself was impossible, for to cross even the smallest distance one must first traverse half of it, and then half again and again, endlessly. Between any 2 points, he claimed, lay an infinite series of divisions. How, then, could motion ever occur? How could Achilles ever overtake the tortoise in his famous race? Zeno's paradoxes were not merely riddles, but mirrors reflecting the strangeness of infinity. They revealed that when the human mind tried to grasp the infinite, it seemed to fall into contradiction. Aristotle attempted to resolve the problem by distinguishing between 2 kinds of infinity. Potential infinity, he said, was endlessness in process. Numbers can always be counted further, distances can always be divided again. But actual infinity, an infinity completed and existing as a whole, he rejected as impossible. To Aristotle, infinity could exist in thought, but never in reality. Infinity in mathematics. Yet mathematics refused to be contained by such boundaries. Euclid, the father of geometry, offered a proof that there must be infinitely many prime numbers. However far one counted, however many primes were listed, more would always exist. Here was a true infinity, not in the world of matter, but in the world of numbers. Centuries later, Galileo would uncover a paradox that shook intuition even further. He showed that the set of natural numbers, 1, 2, 3, and so on, could be paired 1-to-1 with the set of their squares. 1, 4, 9, 16. By this logic, the infinite collection of all numbers was equal in size to the infinite collection of just their squares. Infinity, it seemed, could be compared to itself, and yet remain unchanged. The strangeness deepened in the 19th century, when the mathematician Georg Cantor revealed that infinity was not singular, but layered. There were different sizes of infinity, he declared. The infinity of whole numbers was vast, but the infinity of real numbers, including every fraction, every decimal, every unending sequence, was larger still. Beyond this, Cantor proposed an entire hierarchy of infinities, each greater than the last, reaching toward a horizon that could never be reached. Cantor's discoveries were revolutionary, but they came at a personal cost. His contemporaries attacked his ideas as dangerous, even heretical. Some accused him of overstepping the boundaries of mathematics into theology, for his infinities seemed to echo the boundless nature of the divine. Cantor himself was tormented by doubt, yet his vision endured. Modern mathematics rests on his strange ladder of infinities, a tower of thought rising into the unknown. Infinity in science. As mathematics wrestled with infinity in numbers, science began to confront it in nature. With the invention of calculus, Newton and Leibniz introduced methods that required summing infinite series or dividing intervals without end. Infinity became a tool, not a philosophical abstraction, but a practical necessity for describing motion, growth, and change. In astronomy, the question of infinity turned to the universe itself. Was the cosmos infinite in space? Did it extend without boundary, filled with stars in all directions? Or was it finite, curved, like the surface of a sphere, with limits that no eye could see? Philosophers like Giordano Bruno dared to imagine an infinite universe, teeming with countless suns and worlds. For this vision, Bruno was condemned as a heretic, burned at the stake in 1600. Yet his daring thought planted seeds that would later flourish. Infinity entered physics in stranger ways too. When equations pushed to extremes, dividing by zero, compressing mass without limit, infinities would appear, like cracks in the surface of understanding. Was this the mark of reality itself, or the sign that human theories had broken down? The shock of the infinite. By the dawn of the modern age, infinity had become both a tool and a terror. It enabled calculus, astronomy, and physics, yet it defied intuition. It appeared in mathematics as a hierarchy of paradoxical sizes, in philosophy as a riddle of logic, in science as both necessity and threat. Infinity was no longer a distant idea, but a constant presence, shaping every attempt to describe the world. And with each discovery, the mystery deepened. For if infinity truly exists, in numbers, in space, in time, then reality itself is without end. But if infinity is only an illusion, then every horizon is bounded, every sequence finite, every star and every universe fragile and temporary. The discovery phase of infinity was not its solution, but its birth. From Zeno's paradoxes to Cantor's infinities, from Euclid's primes to Bruno's infinite worlds, humanity had opened a door it could not close. Infinity had entered thought, and it would haunt science and philosophy forever. Infinity had long been a philosophical puzzle, a paradox to be debated by thinkers and mathematicians. But when it crossed the threshold into physics, it became something far stranger and far more troubling. Infinities were no longer curiosities of thought. They appeared inside equations that claimed to describe the very fabric of reality. And each time they appeared, they carried the same unsettling question. Were we glimpsing a real property of the universe, or merely the collapse of human understanding? Hilbert's Hotel, the paradox of endless rooms. In the early 20th century, mathematician David Hilbert devised an unsettling thought experiment that revealed just how bizarre infinity truly is. Imagine a hotel with infinitely many rooms, each occupied. A new guest arrives, and yet the manager can still make space by shifting every current guest into the next room. 1 into 2, 2 into 3, and so on. Room 1 becomes free, another guest arrives, then another 1,000, then another infinite busload. Still, space can be made. Hilbert's hotel demonstrated the unsettling logic of infinity. Even a full infinity can always accept more. In the neat order of mathematics, this was consistent, but applied to reality, it seemed absurd. Could the universe itself operate this way? Could infinity truly exist, or was it only a dream of numbers? Infinity in the Big Bang. In the equations of general relativity, infinity emerges at the very beginning of time. The Big Bang, when traced backward, becomes a singularity, a point of infinite density, infinite temperature, and zero volume. Here, the known laws of physics break down. Infinity does not illuminate, it blinds. To call the Big Bang an infinite point may be less a description of reality and more a signal that our theories fail at the threshold. Physicists suspect that a deeper theory, perhaps quantum gravity, must replace this infinity with something finite, a description of how the universe emerged without resorting to impossibility. Black hole singularities. The same crisis occurs in black holes. According to Einstein's equations, when a massive star collapses under its own gravity, it forms a singularity, a point of infinite density hidden within an event horizon. Here again, infinity surfaces not as an elegant truth, but as a breakdown of understanding. Stephen Hawking once remarked that singularities were where physics ends. To him, they revealed that general relativity, for all its beauty, was incomplete. Infinity, in this case, was not a feature of the cosmos, but a warning, a marker that a more fundamental theory was needed: quantum physics and taming infinities. In the world of quantum mechanics, infinities multiplied like weeds. Early attempts to calculate the behavior of particles produced nonsensical results: infinite masses, infinite energies. The theory seemed doomed until physicists developed a process called renormalization, a mathematical method to sweep infinities aside and extract finite predictions. This taming of infinity was remarkably successful. Quantum electrodynamics, born from renormalization, became one of the most accurate theories in science, predicting values that matched experiments to 12 decimal places. Yet some physicists remained uneasy. Was renormalization a true reflection of nature, or a clever trick to hide infinities we could not resolve? Richard Feynman, one of the architects of the method, famously admitted, "It's a dippy process. We sweep the infinities under the rug and hope they don't come back." The rug, for now, has held, but the problem lingers. If infinity is not real, why does it appear so insistently in our equations? Infinity in cosmology. The cosmos itself offers a larger stage for infinity's shock. Is space infinite, stretching endlessly in every direction? If so, then every arrangement of matter, every possible world, must occur somewhere, repeated infinitely often. There would be infinite Earths, infinite versions of you, infinite histories played out again and again. This idea is not fantasy, but a consequence of certain models of an infinite universe. And yet the concept is so strange, so overwhelming, that many physicists hesitate to embrace it. Infinity multiplies not only stars, but possibilities, until the very idea of uniqueness dissolves. The psychological terror of infinity. Infinity unsettles not only equations, but the human spirit. The thought of endless time raises visions of eternal suffering, infinite boredom, or the eternal return of all events. To philosophers like Friedrich Nietzsche, the possibility of infinite repetition was both terrifying and profound. If you were forced to live your life again, infinitely many times, would you affirm it or despair? In cosmology, too, infinity provokes unease. An infinite universe may sound grand, but it also renders humanity insignificant. One instance among uncountable duplicates, a voice, drowned in an endless chorus. The infinite is not only incomprehensible, it is unbearable. Infinity as a warning sign. Across physics, infinities appear at the boundaries of knowledge, at the heart of black holes, at the origin of the cosmos, in the wild calculations of quantum fields. Each time, physicists suspect they are not glimpsing reality, but the limits of their theories. Infinity, in this view, is not truth but breakdown. This shift is profound. Infinity, once imagined as the ultimate reality, may instead be the signature of illusion. Whenever equations yield infinity, it may be telling us, here lies the edge of understanding, where a deeper law waits to be found. The scientific shock of infinity is that it is both everywhere and nowhere, necessary in mathematics, but intolerable in physics. It opens doors to paradox and collapse, to absurdities like Hilbert's Hotel and impossibilities like singularities. It whispers that perhaps the universe itself does not allow infinity at all, and that what we see in our theories is not the cosmos, but the shadow of our ignorance. The shock of infinity left scientists with a haunting dilemma. Were these boundless quantities real, or were they only artifacts of incomplete theories? To move forward, they had to press deeper, probing the very structure of space, time, and matter. What emerged was a picture both richer and stranger. A universe that seemed to flirt with infinity at every turn, yet one that might be built from finite pieces after all. The shape of the universe. Perhaps the most direct question is the simplest. Is the universe infinite in space? Cosmologists attempt to answer this by studying the curvature of the cosmos. Einstein's theory of general relativity allows three possibilities: a closed universe, finite but unbounded like the surface of a sphere; an open universe, infinite and expanding forever; or a flat universe, poised at the boundary between the two. The cosmic microwave background, the afterglow of the Big Bang, holds clues to this curvature. Measurements by satellites such as WMAP and Planck show the universe to be astonishingly flat, with any curvature so slight that, if space is finite, it must be vast beyond imagination. Flatness tempts many to conclude that the universe is infinite. But here, caution enters. Our observations reach only as far as the cosmic horizon, the distance light has traveled since the Big Bang. Beyond that horizon, the universe may continue without end, or it may curve back on itself, folded in ways we cannot see. Infinity remains possible, but unprovable. Time, eternal or finite. The question extends not only to space, but to time. Has the universe existed forever, or did it begin? Will it last without end, or will it collapse? For centuries, philosophers argued both sides. Aristotle believed time eternal. Medieval theologians insisted on a beginning. Modern cosmology seemed to answer with the Big Bang. Time itself began 13.8 billion years ago. But some theories push beyond. Eternal inflation suggests that while our universe began, the larger multiverse may be eternal. endlessly spawning new universes in a cosmic foam. The far future deepens the puzzle. If dark energy continues to accelerate the expansion, time will stretch toward a heat death. A cold eternity where stars burn out, black holes evaporate, and entropy reaches its maximum. Time may not have an infinite past, but it may yet hold an infinite future. But again, the question lingers. Is infinity real, or are these extrapolations the limits of human imagination applied beyond where they belong? Infinity in quantum physics. At the smallest scales, infinity appears in even stranger guises. Quantum field theory describes space as seething with virtual particles, endlessly fluctuating. But naive calculations predict infinite energy densities, a literal infinity filling every cubic centimeter of space. To make sense of this, physicists introduced renormalization, a method to tame infinities and produce finite results. Yet the underlying tension remains. Do these infinities signal that space-time is not continuous but granular, made of discrete quanta at the Planck scale? If so, infinity is not real, but an illusion created when we try to apply mathematics beyond its range. Loop quantum gravity. One approach to quantum gravity suggests space-time itself is quantized, woven from finite loops of geometry. In such a universe, infinities cannot exist. No infinite density in black holes, no infinite curvature at the Big Bang. Infinity, in this view, is only the shadow of an incomplete theory: entropy and the arrow of time. Infinity also haunts thermodynamics in the form of entropy. The second law declares that entropy, the measure of disorder, always increases. Over infinite time, it leads to the heat death of the universe. But infinite time also raises paradoxes. If the cosmos truly lasts forever, then rare fluctuations must eventually produce ordered states again, even entire new universes. In such a framework, infinity spawns absurdities. Boltzmann brains, self-aware entities arising by chance in chaos, infinitely more likely than ordered universes like ours. Many physicists view these absurdities as signs that infinity cannot be taken literally. If infinite time produces nonsense, perhaps time is finite after all. The cosmic web, fractals without end. On the largest scales, galaxies cluster in a vast cosmic web. Some scientists have asked whether this structure is fractal, repeating patterns at every scale, hinting at infinite self-similarity. Current observations suggest the fractal nature smooths out beyond hundreds of millions of light years. But the very idea of fractal infinity, structures within structures without end, shows how the concept seduces the scientific imagination. Infinity promises elegance, but risks illusion. Infinity as a tool, not a truth. In practice, scientists often treat infinity not as literal, but as a tool. Calculus relies on infinite sums, yet the physical world is measured only to finite precision. Models extend to infinity because the math is simpler, not because nature demands it. Still, the persistence of infinity is haunting. It appears in space, in time, in black holes, in entropy, in the quantum vacuum. Sometimes it produces nonsense. Sometimes it produces predictions of astonishing accuracy. But always, it pushes against the boundary between knowledge and mystery. The question reframed. The deeper we investigate, the clearer it becomes. Infinity is not easily banished, nor easily accepted. It lurks at the edges of science, both indispensable and impossible. If the universe is infinite, then every possibility is real somewhere. Every history is repeated, every dream is lived. If it is finite, then reality is rarer, more precious, bounded by laws we cannot escape. Either way, infinity reveals as much about the human mind as it does about the cosmos. We long for the boundless, even as we fear it. We seek permanence in a universe that may not allow it. And in doing so, we confront not only the structure of reality, but the limits of thought itself. The investigation of infinity does not end here, for as the questions deepen, the mystery escalates. If infinity exists, it reshapes our vision of the cosmos. If it does not, then much of what we believe about the universe may be illusion. The next step is more unsettling still. What if infinity is not just strange, but terrifying? Infinity is not a quiet concept. It does not rest in the margins of mathematics or hide politely in the corners of equations. It spills outward, multiplying possibilities, raising visions both wondrous and terrifying. For if infinity is real, if it truly governs space, time, and existence, then the consequences are staggering. Every thought, every life, every world may not only exist, but repeat endlessly. What begins as a question of mathematics becomes a confrontation with meaning itself. The multiverse, endless universes beyond our own. One of the most audacious consequences of modern cosmology is the possibility of a multiverse. The theory of cosmic inflation, which describes the rapid expansion of the universe in its earliest moments, implies that our universe may not be unique. Inflation may continue eternally in some regions, spawning an infinite number of universes, each with its own laws of physics, its own galaxies, its own versions of reality. In this view, infinity does not lie only in space, but in the very existence of countless other universes. We are not one story in a singular cosmos, but one sentence in an infinite library of worlds. Every possibility may be written somewhere. But the philosophical weight of this is immense. If there are infinite universes, then every version of you exists. One who asked this question, one who never did, one who never existed at all. Infinity multiplies identity until individuality dissolves. Infinite copies, infinite selves. This idea is not mere speculation. It is the logical consequence of combining infinite space with finite combinations of matter. If space is infinite, and matter can only arrange itself in finite ways, then eventually every arrangement must repeat. Somewhere, unimaginably distant, is another Earth, with another you, living the same life in the same moment. Somewhere else, another where everything is almost the same, except for one choice, one detail, one divergence. Infinity gives rise to the nightmare of infinite copies. It erases uniqueness, not by denying individuality, but by duplicating it endlessly. To some, this is exhilarating, proof that all possibilities are realized. To others, it is suffocating, proof that we are not singular, but echoes in a hall without end. Eternal return, the repetition of time. Infinity also haunts time. If time stretches forever, then every possible arrangement of matter will eventually recur. This idea, known as the eternal return, haunted the philosopher Friedrich Nietzsche. He asked, if you had to live your life again and again, infinitely many times, would you embrace it or despair? Physics lends weight to this possibility. In an infinite universe, or in an infinite stretch of time, all configurations of particles will eventually repeat. Our lives, our histories, our civilizations may be reborn endlessly in cycles too vast to comprehend. The eternal return is both terror and liberation. Terror because it suggests we are trapped in an endless loop. Liberation because it reminds us that each moment, however brief, is infinitely significant. Infinity in space-time geometry. Inflationary cosmology adds a deeper strangeness still. The geometry of space-time may be fractal, endlessly self-similar, with structures repeating across scales without end. Universes may bud from universes, worlds within worlds, a tapestry of infinite depth. Mathematically, this vision is elegant. Philosophically, it is dizzying. To live in a fractal infinity is to exist in a cosmos with no boundaries, no center, no final scale. It is to live inside a pattern that never ends, the terror of infinity. But infinity is not only beautiful, it is terrifying. In an infinite universe, every horror is realized as surely as every joy. Somewhere, every tragedy occurs. Somewhere, every suffering is repeated. Somewhere, every mistake is lived again and again. Infinity does not discriminate. It multiplies all. Cosmologists confront this in the paradox of Boltzmann brains, self-aware beings arising randomly in the chaos of infinite time. Given enough eternity, random fluctuations should produce countless brains, each with false memories of a life never lived. If infinity is real, such brains should outnumber ordinary observers like us. And yet, we are here, coherent and stable. The paradox suggests that infinity, taken literally, breaks not only physics but reason itself, the escalation of mystery. At this stage, infinity is no longer a concept to be studied. It becomes a force that destabilizes meaning. If infinity is real, then the universe is not merely vast, but unbounded. If infinity is false, then everything is finite, bounded, and fragile. In either case, our assumptions about permanence and certainty collapse. Infinity demands that we ask questions without comfort. If the universe is infinite, why do we experience this particular moment and not another? If copies of us exist, what does individuality mean? If time repeats, what is the value of choice? If infinities destroy reason, is infinity itself impossible? Infinity does not merely expand the universe. It expands fear, wonder, and meaning. It deepens the mystery beyond comprehension. It whispers that either the universe is endless or that it is finite and fleeting, and either answer changes everything we believe about reality. Infinity is no longer just a number, nor a philosophical puzzle. It is the abyss at the edge of thought, the mirror in which the cosmos reflects its deepest strangeness. Infinity has haunted mathematics, philosophy, and physics for millennia. It lies at the heart of paradoxes. It breaks equations, and it multiplies possibilities until meaning dissolves. But modern physics has begun to ask a daring question. What if infinity itself does not exist? What if every time it appears, it signals the failure of our theories, not a property of nature? In this view, the task of science is not to embrace infinity, but to tame it, to replace the endless with the finite, to trade the unbounded for the discrete. Singularities as warnings, not truths. Einstein's general relativity predicts infinities at the center of black holes and at the beginning of the Big Bang. But many physicists believe these singularities are not physical realities, but the warning signs of incomplete theory. Just as classical physics once broke down at the atomic scale, relativity may break down at extreme densities. Infinity is the red flag, not the reality. In this sense, the Big Bang was not an infinite point, but a transition, a doorway to something beyond our current equations. Black hole cores may not be infinities, but exotic states of matter or new structures of space-time. The infinities are illusions born from our insistence on pushing current laws too far. quantum discreteness, the end of continuum. At the smallest scales, quantum physics suggests a universe that is not smooth but granular. The Planck length, 10 to the power of negative 35 meters, is often considered the smallest meaningful unit of distance. Below it, the very concept of space dissolves. If this is true, infinity vanishes from the foundation of reality. Space cannot be divided endlessly. It stops. Loop quantum gravity takes this further, proposing that space-time itself is woven from finite loops of geometry, like threads in a fabric. Singularities in black holes and the Big Bang are replaced by finite structures. The infinite is cut off at the root. String theory and the holographic principle. String theory, another approach to quantum gravity, imagines that particles are not points but vibrating strings. This smooths away the infinities that plague point-particle physics. Where once infinities arose, the extended nature of strings provides limits. Out of string theory comes the holographic principle, the idea that the universe may be described not by infinite continua, but by finite information stored on a boundary, much like a hologram. If reality is information, then infinity may not exist. Information is countable, finite, bounded. This vision is radical. The universe may feel infinite, but beneath it lies a finite code, a cosmic ledger that cannot stretch without limit, the cosmological constant problem. One of the most troubling infinities in modern physics arises from quantum field theory. When physicists calculate the energy of the vacuum, the so-called zero-point energy of empty space, the result is infinity. Yet the actual observed value linked to dark energy is small but finite. This staggering discrepancy, often called the worst prediction in physics, suggests something is deeply wrong. The infinities of quantum fields cannot be literal. They are signs that our understanding of vacuum, space, and energy is incomplete. Whatever the resolution, it must eliminate infinity and replace it with something measurable. Cosmology without infinity. Some cosmologists speculate that the universe itself is not infinite but finite, even if vast. Models exist where space is curved back on itself, like the surface of a sphere. In such a universe, you could travel forever without finding an edge, yet the total volume would be finite. Others propose that time is finite too, that the Big Bang was not the beginning of infinity, but a bounce preceded by another cosmos. In these cyclic models, infinity is replaced by recurrence. The universe repeats, but not without structure. In both cases, the infinite is replaced with the finite, the boundless with the bounded. Infinity as illusion. If all these speculations point in one direction, it is this: infinity may not exist in the physical universe. It may be a useful tool in mathematics, a symbol of unending potential, but not a feature of reality. When infinities appear, they reveal the boundaries of our theories, not the boundaries of nature. This would be a profound shift. Infinity has long been tied to the divine, to perfection, to the ungraspable essence of the cosmos. To discover it as an illusion would be to replace mystery with finitude. Yet, perhaps this does not diminish the universe. Perhaps it makes it even more remarkable. For if everything is finite, then every star, every particle, every life is not one of infinite copies, but unique, precious, because it will never repeat. The human longing for the infinite. And yet, the longing for infinity persists. Humans reach toward it instinctively, in art, in philosophy, in science. Infinity promises transcendence, a way to escape the limits of mortality. To declare it an illusion may feel like a betrayal of that longing. But perhaps the truth lies not in infinity itself, but in what it reveals. The human drive to push beyond boundaries, to imagine what cannot be held. Infinity may not exist, but the impulse to dream of it is real. It is the mirror in which humanity sees its own hunger for the eternal. Infinity, once the ultimate horizon, may be nothing more than a mirage. But in chasing it, we have discovered mathematics, physics, cosmology, entire worlds of thought. Infinity may be an illusion, but it has been the most fruitful illusion in history. Infinity may be illusion, but science cannot leave the question unanswered. If the universe is finite, where does it end? If it is infinite, how can we know? Across space and time, astronomers, physicists, and mathematicians deploy their most powerful instruments to measure what once belonged only to philosophy. Telescopes, satellites, particle colliders, and supercomputers are today's lenses, bringing the infinite within reach, or showing us its absence. Telescopes at the edge of space. The night sky is the natural theater of infinity, and telescopes are our tools for seeing its limits. The Hubble Space Telescope, staring deep into apparently empty patches of sky, revealed thousands of galaxies in the Hubble Deep Field, structures billions of light years away. These images hint at a universe without edge, one that continues far beyond our horizon. Yet they also show that the observable cosmos is finite. A bubble of space 93 billion light-years across, bounded by the speed of light and the age of the universe. The James Webb Space Telescope, JWST, now looks further still, into the first galaxies formed after the Big Bang. By mapping how galaxies clump, stretch, and dim with distance, Webb helps test whether the universe is spatially infinite or subtly curved back on itself. Its precision may one day reveal whether the cosmos is unending, or whether infinity is only a perception shaped by vastness. Cosmic microwave background, the geometry of the universe. The oldest light in the universe, the cosmic microwave background, CMB, carries the imprint of space's geometry. Missions such as WMAP and Planck have measured its patterns of temperature and polarization with exquisite accuracy. Their findings suggest a universe that is remarkably flat, with any curvature too small to detect. A perfectly flat cosmos is consistent with infinity, but does not prove it. Our instruments can only measure within the observable horizon. Beyond that, we cannot see. The map ends. Whether space continues forever or curves upon itself remains a question hidden in the dark. Particle, colliders, infinities in the smallest scales. While telescopes explore the vast, particle colliders probe the infinitesimal. At the Large Hadron Collider, LHC, protons are smashed together at near-light speed, recreating energies from the early universe. Here, infinity appears as a threat. Without careful corrections, quantum field theory predicts infinities for particle masses and interactions. Techniques such as renormalization sweep these infinities into manageable, finite results. Yet many physicists view this as a sign of incompleteness. True physics, they argue, must eliminate infinities altogether, pointing to theories like string theory or loop quantum gravity, which replace the smooth continuum of space with discrete structures. If space and time are quantized, then infinity may be mathematically elegant, but physically unreal. Black hole observatories, singularities under the lens. Black holes are the laboratories of infinity. At their centers, relativity predicts singularities, points of infinite density, But do such infinities exist? To answer, scientists use new instruments. The Event Horizon Telescope, EHT, produced the first image of a black hole's shadow in 2019, revealing the swirling matter at the edge of space-time collapse. Future observations aim to test whether general relativity holds near the event horizon, or whether new physics prevents infinities from forming inside. Gravitational wave detectors like LIGO and Virgo add another tool, listening to the ripples produced when black holes merge. These waves may carry imprints of physics beyond relativity, clues that infinities are not real but replaced by finite quantum states. Supercomputers and simulations. Beyond observation, supercomputers allow us to test infinity through simulation. Programs like the Millennium Simulation or Illustris model billions of galaxies across cosmic time, probing how structure emerges from dark matter and dark energy. These simulations rely on finite resources, yet they reveal whether infinite assumptions are necessary. For example, do galaxies cluster in fractal patterns without end? Or does order smooth out beyond a certain scale? Thus far, evidence favors the latter. The universe appears finite in its patterns, even if vast in extent. Dark energy and the fate of the universe. Infinity is also tested in the cosmos's future. If dark energy continues to accelerate expansion, space will stretch toward a heat death, a form of infinite time. Observatories like the Vera C. Rubin Observatory and ESA's Euclid mission seek to measure dark energy's behavior with precision. If they find dark energy to be constant, the universe may expand forever. If it changes, infinity may be cut short, in a collapse, a rip, or a fade into nothingness. Infinity, in this sense, is a hypothesis testable through the behavior of galaxies themselves. Mathematics as a laboratory. Infinity is not only probed in telescopes and colliders, but in mathematics itself. Set theory continues to evolve, exploring Cantor's hierarchy of infinities and their paradoxes. Computer science, with its emphasis on discrete systems, challenges whether infinities are necessary at all, or whether reality may be modeled entirely through finite computation. Mathematics builds infinities, physics tears them down. Between them lies the central tension. Is infinity real, or is it only a symbol of human abstraction, the human position? For all our tools, one fact remains. Infinity, if it exists, may always lie just beyond our reach. Our telescopes can only see as far as light has traveled. Our colliders can only probe as deep as energy allows. Our equations can only stretch as far as thought will carry them. And yet, the search continues. Infinity is tested not because we expect to hold it, but because in chasing it, we expand the boundaries of knowledge. Each instrument, each experiment, each simulation is a gesture toward the unbounded. Science has brought infinity down from the heavens into laboratories, colliders, and computer screens. And still, the question lingers. Each test, each observation suggests the same haunting truth. When infinities appear, they are warnings, not realities. Perhaps infinity is not written into the fabric of the universe at all. Perhaps it is only written into the human mind. Infinity has followed humanity like a shadow. It haunted the minds of Greek philosophers, dazzled mathematicians with paradoxes, and broke the equations of physicists. For centuries it seemed inescapable. The night sky appeared boundless, numbers marched without end. Time seemed eternal. To think was to stumble into infinity. And yet, after all this pursuit, science is beginning to whisper a different possibility, that infinity itself may be an illusion, the fragility of boundlessness. If infinity is not real, then the cosmos is not unending, but vast and finite. Space may curve back on itself like the surface of a sphere. Time may stretch long, but not forever. Black holes may not conceal infinities, but finite cores shaped by quantum laws. The revelation would be profound. Infinity has always carried an aura of divinity, of perfection. To deny it is to accept limits, boundaries beyond which nothing exists. But this does not make the universe smaller. On the contrary, it makes it more precious. Finitude transforms the cosmos from an endless repetition into a singular, irreplaceable story. The human longing for the infinite. Why, then, has the idea of infinity held us so tightly? Perhaps because it reflects our own longing to escape boundaries. Infinity promises permanence in the face of mortality, scope in the face of smallness. To imagine the infinite is to imagine freedom from every limit. But the human mind is finite. Our lives are finite. Our world is finite. The pursuit of infinity may reveal not the structure of the cosmos, but the structure of our desire. The infinite is not reality, but the mirror of our hunger for the eternal, the beauty of finitude. If infinity is illusion, then the true wonder lies in the finite. Stars shine not forever, but for billions of years. Planets orbit for eons, then decay. Life blooms, then fades. Each moment, each configuration, each existence is unrepeatable. Infinity cheapens uniqueness. In an endless cosmos, every event repeats endlessly. Every life occurs infinitely often. But finitude restores meaning. If the universe is finite, then this moment is singular. This life, this planet, this cosmos. Each is one of a kind, never to return. The beauty lies not in endlessness, but in fragility, the silence of the night sky. Imagine a night sky where infinity is illusion. Beyond the cosmic horizon, there are no endless repetitions, no infinite Earths, no eternal cycles. There is only what exists, a galaxy here, a star there, a fragile scattering of light against darkness. Does this make the cosmos less? Or does it make it more miraculous, that such beauty, such scale, such order can exist at all? Not forever, but once. In silence, infinity dissolves, and what remains is the finite radiance of being. The final reflection. Infinity, real or not, has shaped us. It has expanded thought, driven mathematics, forced physics to confront its limits. Even if it is illusion, it has been the most fruitful illusion in history. It has taught us that in chasing the unbounded, we discover the boundaries of knowledge. Perhaps this is the gift of infinity, not to exist in reality, but to exist in imagination. To remind us that the human spirit is restless, always reaching beyond what can be held. And so the final question lingers. Is infinity illusion or reality? We may never know, but perhaps it does not matter. For whether the universe is infinite or finite, our place within it remains the same, fragile, fleeting, and luminous. Infinity may not be real, but wonder is. And in the end, wonder is enough.